Hello everybody, in this video we're going to be discussing section 10.4 in our text entitled Phase Diagrams. First I want to do a little review from last section. During phase changes the temperature remains constant. If energy is being absorbed in the phase change, then all of this energy is being used to break the intermolecular forces, not increase the temperature of the substance. If energy is being released during the phase change, then all this energy released is coming from the formation of intermolecular forces, not from the decrease in temperature of the substance. Okay, so when we have components of two phases in equilibrium, we're not going to see a difference in temperature. All right, a glass of water with ice in it is going to stay at 0 degrees Celsius so long as there's still water and ice present. Okay, it doesn't matter how much ice there is versus water, it will still be the same temperature. Phase diagrams, these are graphical representations of the phases at different pressures and temperatures. These can be calculated to some degree, but are often found just through experimentation, where we do like a series of experiments basically under different conditions to see where these temperatures and pressures lie. And we can see that basically what we wind up with is some regions. So everything in this region is a gas, everything here is a liquid, everything here is a solid, and the boundaries here represent the various different phase changes. We can also see that at low pressures and temperatures is when we see that more exotic changes of sublimation and deposition. And we also have two important points I want to point out to you here. The first is the triple point. This is the temperature and pressure where solid, liquid, and gas exist in equilibrium. So things get a little bit trickier here. We have three different equilibriums to consider. This can actually happen for water on the planet. It happens in like Antarctica and stuff, where we have liquid water, ice, and gas all in a equilibrium. And the next one is the critical point. And the critical point is up here, and it is the point above which everything exists as what we call a supercritical fluid. Okay, so this is kind of a new phase of matter that we're introducing to you guys now. Basically, when temperatures and pressures are very, very high, we wind up not having anything that we can call a gas or a liquid or a solid, but instead we have these supercritical fluids. Let's talk a little bit more about that critical temperature and pressure. So above the critical temperature, a gas cannot be liquefied no matter the pressure. All right, and that critical temperature would be if I took the critical point and I traced it down to the temperature axis right here. So this would be my critical temperature. The pressure required to liquefy a gas at its critical temperature is the critical pressure. So if I track this point over to here, this is my critical pressure right here. And I have here listed some critical temperatures and pressures for various different substances. If you go on to study like chemical engineering and stuff, these start to become more and more important, even in physical chemistry, as like normalizing factors that you're going to see in a lot of different equations. So it's important to understand where these values are coming from. Let's talk a little bit more about supercritical fluids. Supercritical fluids, they expand to fill their containers like gases do, but their density is much higher than typical gases. They are capable of dissolving non-voluble solutes, so much like liquid water can dissolve salt, for instance, a supercritical fluid is able to dissolve those types of solutes, where gases typically only want to dissolve more volatile solutes, like liquids and stuff. They essentially have no surface tension and very, very low viscosity. So what that means is that they're able to readily permeate substances and materials and stuff and get into very small pores. These types of properties make them extremely useful solvents for many applications. Supercritical CO2 extraction is used widely in industry, as is supercritical water extraction. Even though you have to put in a lot of energy to get the pressures and temperatures high, the advantages of using these supercritical fluids tends to outweigh that. There are some other properties that can change depending on the identity of the fluid. For instance, supercritical water has a low dielectric constant, which means that supercritical water, liquid water, would be what we would call a polar solvent because it has that dipole, but supercritical water actually tends to act more like a nonpolar solvent, which can be really, really useful because then you can use something that's pretty innocuous like water as opposed to some of the more and less environmentally friendly organic solvents if you do it under supercritical conditions. In conclusion, phase diagrams are useful representations for visualizing the phase of a substance at a specific temperature and pressure. The triple point and critical point can be found on a phase diagram, and supercritical fluids have important properties that differ from solids, liquids, and gases.